Anyway, I would like to thank Harry and Garrett and Koji-san for organizing this. I had the opportunity to see a couple of familiar faces, my old friends, and lots of really new faces, which I hope to make more friends during this conference. So the purpose of this talk is trying to give you a brief introduction to this new field that can either be called as spin Cavitronics or simpler as cavity Spintronics. But before I do that, let me first introducing you the people who are working with me. Li Hui, Bi Mu Yang, and Yong Sen Gui. These are three assistants in my group. And in fact, Bi Mu Yang and Yong Sen Gui are now in the audience somewhere at the backside of the conference. And Michael, Paul, Jing Wei, and Yang Ying, these are for graduate students still working in my group. I should also thank IEEE Magnetic Society because this year they're supporting me traveling around the world, talking to people and broadcasting our work in this new field of cavity Spintronics. My plan is quite simple. As an introduction, I would like to give you a relatively simple story about the overview of this new field. During the week, we have real experts in the audience who will give really exciting talks that I myself are eager to learn. So I will begin with the physics of a new quasi-particle, which we call as the cavity magnum polariton. It's a very nice particle. I will tell you the basic physics picture of that and why it is useful. Then I will tell you, by creating this quasi-particle and using that, there is actually a price to pay. And we are stuck in a certain regime, which many of us are trying to escape. And so far, there are three ways developed trying to escape out of that not so well situation. And at the end, I will give you my perspective of the cavity Spintronics, where it goes, and what kind of path we may take. So that's the basic idea. Since many of you probably travel, like me, a long distance here, you're probably still suffering from jet lag. In case you fall asleep, please remember this graph, and that's the whole context of this talk. Essentially, what I'm going to tell you is the story about a hybrid beast named cavity magnum polariton. It happens when you lock in photons, in this case microwave photons, together with spins in one dark room, which you call as cavity. And then, if the interaction between photon and spins are strong enough, then they will do something unspeakable, produce a hybridized beast, which is no longer photon, no longer spin, but in the same time have the spin characteristic and the photon characteristic. Because of that, this hybrid beast can talk to both species. It can talk to the spin systems, it can also talk to the photon systems. That is why this hybrid beast becomes very useful. And the cavity Spintronics, the field, is essentially, so far, about this using this hybrid beast. And this beast is growing very fast. And I will tell you the reason why it is that. Well, this beast was created by using cavity techniques. As many of you know, cavity techniques is really a kind of disruptive technique. When people using that technique to certain fields, it always causing tremendous change of that field. For example, people used the cavity techniques to study atoms. And then these two gentlemen get the Nobel Prize in 2012 because of many interesting physics emerged by studying the strong coupling between photon, in this case optical photon, with atoms. And there is a field which is still growing very well. That is people using cavity technique combined with mechanical oscillators. and produce a lot of very useful technology, particularly for quantum applications. Speak about quantum applications, many of you probably know this famous work done by groups in Yale University, where people are using microwave cavity combined with superconducting qubit, and by using that, you can produce a lot of applications for using quantum information, as many of you probably know. So in that perspective, it is a little bit surprising in retrospect that the cavity techniques have been only recently applied to the system where we have magnons and many spins. And in fact, people do using cavity, microwave cavity, as an experimental tool to study spin dynamics, but the strong coupling between microwave photons in a cavity and the spins, this phenomenon was really started a few years ago, which I will tell you who made the contribution of that. So the story really, the cavity story really begins a long, long time ago. And in the old days, people studying the physics of one single atom put inside in a cavity. And atoms can be viewed in the simplest way as a two-level system. Essentially, it's the same as one single spin. Then if there is a strong coupling between the spin and these cavity photons, you can write down the Hamiltonian in these three parts. The first part is essentially the single spin Hamiltonian. And the second part is your cavity photon with the mode frequency of omega 0. And if there is a strong coupling between spin and photon systems, the coupling can be described by using this parameter G, which people call as the Rabi frequencies. And you want to create a system where this Rabi frequency is as high as possible, so that these two systems coupled strong. And for the single spin or single atoms, the Rabi frequency is quite low, typically at the order of 1 Hz. If you put that coupling strength in the context compared with the damping dissipation of these two systems, the spin system and the cavity system, which have the damping rate gamma for the spin system and damping rate K for the photon systems, then you are talking about the cooperativity. The cooperativity is the coupling strength squared divided by the product of the damping. For a single spin system, and the cooperativity is again very low. It is at the order, typically at the order of 1. So a few years ago, some prophets made the prediction, or the idea comes from some people saying, we should probably try with many spin systems instead of these single systems in order to enhance the Rabi frequency or enhance the cooperativities. And magnons, of course, is very familiar for this community, I think. Essentially, if you have a many spin system, like a ferromagnetic systems, you have many, many spins which are locked together due to the exchange interaction between them. So that you have the dynamic of one spin, it will impact the dynamic of all the other spins, forming a kind of wave, like the lattice wave, where you have phonon, but in this case you will have wave, which gives you magnon. It's the energy quanta of this connective spin excitation. So the idea is, if we produce a system, lateral magnons strongly coupled with cavity photons, what's the benefit we can get from such kind of systems? And the prophet, I think, will probably arrive this afternoon, and we can listen to a talk by himself. Essentially, they have predicted in 2010, saying if you're using magnons, then you can raise this coupling rate. Remember, the single spin is 1 Hz. If you're using magnons, you have the capability of raising these coupling rates up to terahertz. And that is, of course, very exciting for many people. So starting from 2010, a few groups started trying to do the experiment, including my group. We were doing that experiment, but unfortunately, there is another one in the audience who beat us. That is Hans Huber. His group was the first group who really succeeded in this kind of experiment. And this after this talk, we will hear the talk of Hans, in which Hans basically put a piece of ferromagnetic insulator made of yin, put that yin inside a special cavity. In his case, it's a planar cavity, but for simplicity, I just use this figure. In that system, you are simultaneously exciting a huge number of spins. And in fact, the number of spins in his system is up to 10 to the power of 16. Then, because all those spins are coherently locked together in a magnetic excitation due to the exchange coupling, indeed has found that this Rabi frequency is significantly boosted. Theoretically, you can calculate that. You will find out the Rabi frequency of the main spin system is enhanced by square root of the number of spins you have in your magnetic excitation. Because the number of spins in this bulk yin material is so large, has demonstrated that at 50 millikelvin you can get a Rabi frequency of 100 megahertz, almost terahertz. If you use a little bit large sample, you will easily get to the terahertz. And if you calculate the cooperativity, he found that the cooperativity is larger than 1,000. It's again a significant enhancement. So that work is really the pioneer work of this field, and it demonstrated what the prophet said is indeed made sense, and indeed we can measure this kind of very strong coupling between many spin system with KVT photons. Now, to give you a very simple picture of what happened in terms of the physics, you can think about that now you have a many spin excitation. Essentially, this is the spin operator for all the spins in your yin. And certainly you still have KVT photons. Now you will have a coupling term determined by the single spin Rabi frequency. But because now you have a collective spin operator, this effective coupling is actually significantly enhanced. That's the basic physics of that. Without this coupling, what you can have in your system is the photon excitation. You create one photon, which gives these KVT photon modes as point omega c, or you can have the one magnetic excitation. You're exciting your spin system from ground states to the magnetic excited states. Let's call this excitation energy essentially is the magnetic frequency, which you can use in the external magnetic field to tune that. With coupling, you have to take into account of the coupling of both systems. Then you will have a combined sort of ground states, where you don't have any excitations. But now you can have two types of excitations. You can have excitation of, let's say, one magnetic excitation, or you can have excitation where you have one photon excitations. Because of this coupling, these two types of excitation must be hybridizing. And if you take into account this kind of hybridization, you will have produced this kind of hybridized states, depending on the magnetic field you apply. So that you will have a situation, if you tune in your magnetic frequency, like this curve, by using the external magnetic field, when your magnetic frequency approaches this photon frequency, these two types of excitation will no longer independently crossing with each other. Instead, they have to mix together to give you these hybridized transitions. So you will typically see this kind of so-called anti-crossing spectrum. And from at the position where you have so-called detuning equals to 0, which means the maximum frequency equals to the cavity frequency, you look at the splitting of this anti-crossing spectrum, you get the measure of this Rabi frequency. In this case, it's no longer single spin Rabi frequency, but the many spin system like Rabi frequency. And if you look at the scale, this is the gigahertz. And indeed, the typical Rabi splitting for this many spin systems coupled with photon is at the order of, say, 100 megahertz. So significantly enhanced compared with the single spin of 1 hertz. That is why people get very much interested in these systems. Now, of course, you can imagine if you're moving from a single spin system to a many spin system, you anticipate that the correspondence principle should apply. That means this coupling phenomena very likely not only can be explained by this quantum picture, which I just told you, but very likely there existing an equivalent classical picture to understand that, as the correspondence principle tells us. And that is in fact true. So I will spend a few minutes to explain to you the equivalent classical picture of understanding this magnetic spin pattern. To do that, if we look at the microwave cavity, the simplest way to understand the microwave cavity is that we understand as if this microwave current follows this LCR resonant equation. You're using LCR circuit to describe your microwave cavity. And in fact, engineers all the time doing that kind of thing. And if you write down your LCR equations, you solving that, you get a kind of resonant mode for your microwave current, which is essentially your cavity mode. And your cavity mode frequency is determined by the equivalent L and C parameter of your cavity. And you will certainly have certain dissipation, in this case determined by this resistance parameter of your cavity, which determines the line width or the quality factor of your cavity. That's the simplest engineered type of description, classical language for the cavity analysis. And you can think if you have a microwave current, the Ampere's law tells us this microwave current must be related with a microwave magnetic field, because we are going to deal with spins. And the phase of the microwave magnetic field is locked with the phase of the microwave current. That is essentially what Ampere's law tells us. So remember that for one fact. The second fact is, if we're thinking about the spin dynamics inside a Jaeger material, and that we are familiar can be described by this Landau-Lifshitz equation. And in the case that this dynamic is at the linear dynamic regime, we can linearize this Landau-Lifshitz equation, and essentially we get a resonance, also a resonance, which is now determined by the magnetic frequency, or the ferromagnetic resonance frequency, with certain damping, determined by the so-called Gibbs damping parameter. That's the simplest picture, semi-classical picture for understanding the spin excitations in the ferromagnetic material. Now, there is a very important fact we always neglect if we're doing the ferromagnetic resonance experiment. And that effect is that if you have spin dynamics, then you have a changing magnetic momentum. And this changing magnetic momentum is actually going to producing a high frequency voltage. And this high frequency voltage is actually going to backacting on your microwave field. Normally when we're doing ferromagnetic resonance, we don't care about that. All we care is how the microwave is impacting the spin dynamics. However, if you put in this ferromagnetic material inside a relatively high quality cavity, this back action is something you have to take care of. Essentially what you will have if you put in these two systems together is that on the one hand, this microwave current is going to produce a microwave magnetic field which applies a torque on the spin, driving the spin dynamics. That's what we do when we're doing FMR experiment. Now, because this cavity has relatively sharp mode spectrum, relatively sharp photon density of states, it can very sensitively pick in the back action of the spin dynamics acting on this LCR circuit. In other words, this back action due to the spin dynamics on the microwave field becomes important. So if you take into account of this action and back action, then your LCR equation and your LLG equation becomes coupled. They are no longer independent. You have this very simple 2x2 matrix which tells you this photon microwave dynamics is coupled with the spin dynamics. And if you solve in this eigen equation, you will get an eigenmode which is no longer purely microwave field, no longer purely spin dynamics, angular momentum, but it is a phase coherent superposition of both. That will be your eigenmode. And in fact, this is this classical picture telling you that the microwave field and the spin dynamics are coherently coupling together, give you a quasi-particle, which we call as the cavity magnon polariton. So that's the classical picture of the magnon-photon coupling, which gives you the cavity magnon polaritons. Just to give you a perspective, the polariton is something that solid-state physicists known for many, many years. And essentially, you can understand the Maxwell equation links two types of dynamics. On the one hand, the Maxwell equation gives you the electrodynamics. On the other hand, in the Maxwell equation, you have material parameters. So that if the waves are propagating in solid materials, you will have the other type of dynamics. Could be charge dynamics, could be lattice dynamics, could be spin dynamics. And the Maxwell equation very coherently links these two dynamics, and that is why you have many different types of polaritons due to this type of links. The most famous one is, of course, the phonon polaritons, which is essentially due to the fact you have the phonon dynamics, lattice dynamics, determined by the TO phonon and LO phonon. If you mix these two equations together, you get this hybridization. No longer you have pure light or pure photon, but you have a hybridized excitation, which is the polariton waves in your solid. And polariton, therefore, is quite ubiquitous phenomenon. And in fact, it depends on what kind of dynamics are mixing with the electrodynamics. You can have polaritons related with charge dynamics, such as plasmons and extron polaritons, or you can have polaritons related with lattice dynamics, these famous phonon polaritons. And in the field of magnetism, in fact, the fact of magnon polariton is something the community have been knowing that for many, many decades. What is really new here, this community study, is this cavity magnon polariton. You are putting this magnetic material inside a cavity, and because of this spatial density of states of the photon in the cavity, you get very interesting phenomena related with this cavity magnon polariton. And in my opinion, this new type of magnon is very similar to the cavity exciton polariton that the semiconductor community has been studying for decades now. And in fact, just this week, there is a parallel conference taking place focusing on the field of cavity exciton polaritons in the optical cavity frequency regime. And if you look at that, we just have the spin Cavitronics 1, and that community actually have their conference to the 19th. And I myself was very much eager to attend that conference, so I tried to convince them to postpone that conference for 1 week, but it didn't work. They choose the same week as we do. Perhaps next time, spin Cavitronics 2 or 3, we may see putting these two communities together. That will be very fun. We can learn a lot of existing technique and existing ideas from the semiconductor people who study the cavity exciton polaritons. They're already paying attention to what is going on in our community. That's a good thing. So how do you measure that, this quasi-particle, this beast? Well, experiment turns out to be very simple. If you have a cavity, for example, this one is the cavity we use in my group, you put yield inside the cavity, then you're simply doing a microwave transmission experiment. You will see this resonance. This is your cavity mode at the 10.56 gigahertz. You're using external magnetic field to tuning your magnetic frequency. And you see when this magnetic frequency approaches the cavity frequency, anti-crossing happens. And this experiment is done at room temperature. So you see that even at room temperature, you have very large Rabi frequency at the 100 megahertz size, and you have very large cooperativity even at room temperature. No surprising, because as I told you, the phenomena can be very well understood from the classical picture. So at the room temperature, the classical coherence tells you that this kind of property is possible. So what's the use of this body particle? As I told you, it is essentially a beast that speaks both languages. It speaks the language of the spin, it speaks the language of the microwave. So it produces a very effective link between cavity photon with the spins. There is a bridge built by this quasi-particle. And that is why this quasi-particle becomes a great transducer. Because each of the systems, spin and a photon, can be further linked to other systems. For example, we will hear a talk on Friday, I think, that people link the microwave cavity with qubit. And once you do that, you produce an indirect link between the qubit and the spin, so that the quantum information in your qubit can be transferred or read by the spin system. One example. All people also in the audience have done beautiful work that links this spin system with visible light photons. Then you produce a link from the visible light photon through the spin with the microwave photon. You produce a kind of new type of router that allows you converting photons from visible light frequency to the microwave frequencies. And in my group, we are focusing very much of using this link to manipulate the spin current. And also people have realized that using that, you can produce a link between the optical bistability with the magnetic bistability. And the bistability is very useful for producing many different devices. So there will be many more to come in the next few years, because seems to be that you have many possibilities of using this new bridge to create new links. And on Friday, we're going to hear Koji-san talking about very likely something related with that. And tomorrow, we will have 3 talks actually focusing on these photon routers. So therefore, I'm not going to say anything about those beautiful works. Instead, I will very quickly give you a sense how can you using this new quasi-particle to produce a way to manipulating spin current. That is, I'm going to do now. So spin current is again something very familiar to this community, I think. One of the good ways of producing spin current is using the effect of the spin pumping. What you need is a bilayer device where you have ferromagnetic material connected with normal metals. Then you shine microwave. Essentially, you produce this processing non-equilibrium magnetization. Now, because you have an interface here, if you're using microwave to produce this non-equilibrium magnetization, it is going to diffuse into the metal. Just like you have a droplet of oil into the water, you will have the diffusing effect. In this case, you will have diffusing of this processional magnetization, which contains a time-independent part and a time-dependent part. Because these are non-equilibrium magnetizations, they are spins. So in this way, you're producing DC and AC spin current. That is what people call AC spin pumping. And you immediately see this kind of device is very similar like a semiconductor solar cell. In the semiconductor solar cell, you have PN junction, and you have electron and holes. If you're using sunlight to producing non-equilibrium electron and holes, they are going to diffusing across the interface, give you a voltage. That's the semiconductor solar cell. In this case, it is like a spin solar cell. It's not really solar, it's a microwave. What you have is that microwave producing non-equilibrium spins. You again have two types of carriers, spin up and spin down, like the electron and the holes. Then the diffusing of this non-equilibrium spin gives you the spin current. So this spin pumping device is something like the spin solar cell device, if you like, in the simplest way. This is what the community have been doing for decades now. We are familiar with that. The experiment we have done is that we take two of these spin solar cells, and we let both spin solar cells couple with the same microwave cavity mode. So in this case, this microwave is not just generating the spin current, it also serves as the function of linking these two spin solar cells in a coherent way. So you can easily imagine you were producing this kind of coupled system, that a new type of, a slightly different type of cavity magnetic polariton, where you have the magnetization dynamic of one of your spin solar cell, you have the magnetization dynamic of your second solar cell. They are linked by the microwave cavity mode. Now, because of this bridge linked by this magnet photon coupling, you can imagine if you controlling one of your magnetization to locally tuning your spin current in one of your device, through this link, you might have impact to the second device, which is located far away from the first device. In our case, we put these two devices centimeters away in the same cavity, so that between these two spin solar cells, there is no direct interaction at all. It's centimeters way too long for any magnetic interaction. But we demonstrate if you locally manipulating the spin current of one of your devices, you simultaneously measuring the spin current locally of the second device, you see very effective control due to the changing of the spin current of one of your devices. So in this case, essentially by using the cavity magnetic polariton, which build a link between spin dynamics with the microwave, you take this link back to the second device, you achieve a case of using one spin current to almost switch on and off the spin current of the other device. That's just to give you an example why this type of new link becomes very useful in the field of the spintronics. So all these are wonderful, but there is no free match. When you gain something, you typically lose something. And now I'm going to talk about the price we pay for that. And what we essentially have done is that we're moving from a single spin to many spin system. And if you think about that, this is very much against the tide, because the priest told us we should go down to the single atom or the single spin systems. But in this field, we are actually doing the opposite. We are coming back from the single spin system to the many spin system. The reason we do that is because, as I told you, this many spin system enhances significantly this Rabi frequency. It gives you a very large cooperativity. That's the good thing we want. But by doing that, we actually lose something. And the thing we lose is the so-called nonlinearity. What it means is that if you have a single spin system, you essentially have a two-level system. And that, for the quantum information guy, people say this is an extremely nonlinear system. Which means if you have one photon, you get the system already saturated. If you have a second photon comes in, the system has no choice but to enhance its Rabi frequency. So what you see is that due to the nonlinearity of the single spin system, the Rabi frequency is actually scales with the square root of the photon number. So that people often in the quantum field using the number of the photon to control the Rabi frequency. That's because of this nonlinearity of the single spin systems. But once you come to the many spin systems, that capability totally lost. So all the groups, my group and many other groups in the audience, experimental groups, we have done many experiments. We're measuring these Rabi frequencies and we're changing the microwave power, which means you're changing the number of photons. We always see the Rabi frequency is not changing, no longer controlled by the photon number. And the reason is because when we move into the many spin systems, we actually come back to the very limited linear dynamic regime. In our systems, the number of KVT magnum polariton, or non-equivalent spin, excited by microwave photon, is much smaller than the total spin number. So you are in the very limited linear dynamic regime of the spin dynamics. Because of that, you lost completely your nonlinearity in this kind of coupled system. And by losing that, we can no longer control the Rabi frequency by changing the photon number or microwave power. That's one way to see it. The second way to see it, the same thing, is that if you're thinking about a single spin system, that system, because of its nonlinearity, is very sensitive to the photon number. If you think about the photon number states of n, that states will see a two-level system get coupled and split into two due to the Rabi splitting. The spin of the photon number n plus 1 will also see the two-level system and also get split due to the photon spin coupling, and you have the Rabi splitting. As I told you, this Rabi splitting square root of the n. So if this n of the photon number is very large, essentially this splitting is almost equal to flat splitting. So if you think about doing spectroscopy of this single spin system, which people have done a lot of experimenting in other fields, atomic system, quantum dot system, diamond single spin system, you can easily see you will always produce 4 transitions. 2 of them will have the same frequency, which is equal to the original photon mode, omega 0. In other words, you will have a triplet in your spectrum. You have a mode appears exactly at your photon mode, and you have 2 side bands determined by this Rabi splitting. This is very famously called as the Muller triplet. If you're doing single spin spectroscopy of quantum optics, that's the characteristic spectrum you always see. And it tells you that you have access, your system has access to the photon number states due to the nonlinearity. However, as I already told you at the first part of my lecture, in our systems, we don't see Muller triplet. Instead, we always see these twins, these anti-crossing twins. And that is exactly because our system are reduced to this very small fraction of linear dynamical regime. We lost the access to the photon number states because we have this linear system, dynamic system of our magnetic systems. So many people have been thinking in the past few years, finding ways to reintroduce nonlinearity into this magnon-photon coupled system, this many-spin coupled photon system. And there are at least 3 paths developed. Perhaps there are more. I hope to learn from this community. One method is the Tokyo University Produce Science Group did. Essentially, they coupled this polariton system with an extremely nonlinear system, which is cubic, transmode, totally nonlinear. By introducing this additional coupling, they inject the nonlinearity into this coupled system. That's the one way you do. And the second way you can easily thinking of the way is now you have coupled system of photon and spin, magnet. Magnon is a system we can easily introduce in nonlinearity. If we drive in the precession angle larger, then we essentially have the nonlinear magnetization dynamics. So the hope is that if you go to that dynamic regime, due to the coupling with the photons, you probably can introduce nonlinearity into the system. And that is true. And in fact, tomorrow, Yong-sen is going to give a post describing the effect over there. And you can see, in principle, it works. But there is also no free lunch. By doing that, the very complex magnetization nonlinear dynamics sets in, makes the system much more complex to understand. You can have a lot of the detailed study experimentally from the post. So what I'm going to introduce to you in the next few minutes is using the optical side by using a new type of cavity technique, which we call active cavity technique. I'm going to show you by using that. You can also introduce nonlinearity into the system without making the system messy and complicated. That is what I'm going to show. So this active cavity technique will produce a new species, which is no longer cavity magnon polariton, but what we call as cavity magnon quintuplet. So what is it? Well, we know how to produce cavity magnon polariton. Put a lid on top of a planary cavity, for example, then strong coupling sets in, and boom, you produce this beast. That's cavity magnon polariton. And in fact, you produce many of them, but there is no phase correlation between them. They are independently produced by a microwave. Now, what we did is that we're collecting the microwave leaked out of this first cavity using a second cavity, which is designed to couple with the first one. And in this second cavity, we introduce an amplifier which coherently enhances the microwave current or enhances the number of the photon, then feed this coherent photon back to the first cavity. In this way, I will show you that you have a very different situation. You no longer have one beast or beast randomly playing with each other, but you have a situation like sometimes you see in the nature when you have many beasts dancing, flying together, they show some unspeakable beautiful pattern. And that is what we see in our device. And here is the spectrum we measured in this active cavity system coupled with Ye. And you see, now you no longer have these twins. Instead of twins, you actually have 1, 2, 3, 4, 5 transitions. And they are beautifully aligned. So that if you look carefully, they actually form 2 sets of triplets. This is one set. And there's another set of triplets. They share with the central node of the cavity photon node. And in other words, in this system, you actually reproduced the Muller triplet. And not just one set of Muller triplet, but 2 sets of Muller triplet. As I told you, Muller triplet is a signature that you have the access to the photon number states. Very likely you have the photon number control of the Rabi splitting. And that, if we carefully do our experiment, you measure in the Rabi splitting, essentially splitting here, by changing your gain, which means you're changing the feedback number of photons. Indeed, we see the Rabi splitting now is tuned by the number of photons. This is wonderful because remember we have many spin systems. We don't have a single spin system. Ideally, theoretically, we still have a linear dynamics, but due to this active cavity, we actually introduce, very surprisingly, nonlinearity into the system so that we can access to these photon number states, restore the photon number control of the Rabi splittings. And the cooperativity at room temperature in this case can be tuned by the photon number in this experiment by almost a factor of 2. And you can describe that using the term quantum information guy in the other field actually knows about that, is so-called dressing of the dress states. In the simple language, what happens is that I told you, you can have magnetic photon coupling producing these polariton states. You can also call those polariton states as dressed states. Spin is dressed with photon. Now this active photon feed back to the cavity actually sees these dressed states. And because they are coherent photons, they will couple with those dressed states once more. This second order of coupling produces 2 sets of Muller triplets, which you can accurately describe using a Hamiltonian based on this picture, and that produces the dispersion exactly as you measure. So in this way, indeed, it shows you that this active cavity technique provides us a free lunch. And this free lunch is that you have a manual spin system where your Rabi frequency is significantly enhanced, and you reinstalled the nonlinearity into that system, give you this photon number control of the Rabi frequencies. And you ask yourself why that is possible. Well, the answer is quite simple. If you know the Phil Anderson's second philosophy, there are plenty of rooms at the bottom in the small system, there is an opposite philosophy tells you in the solid state system, there are plenty of surprises in the many body systems. And in fact, he wrote a very famous paper, which is very enjoyable to read, published in Science many years ago, said, more is different. That tells you that many body system is a very, very hard to follow. So with that, I'm coming to the end of my talk. The take-home message 1 is that I think many of us is thinking of this new field, cavity spintronics, going quantum, which is follow the priest-female. Certainly very exciting and definitely worth to do. There is, what I'm trying to say is, there is slightly ignore the second path, which I call go many body. Because go many body, there are a lot of exciting, surprising things, as our experiment tells you. And in fact, if you think about it, what is this cavity magnetic? It essentially tells you more spin is better than a single spin. Go many body. Because if you have many body spin system, the Rabi frequency is significantly enhanced, as Hans and Michael Flaque they told us. And what I showing you is telling you that more this beast is better than a single beast. In our experiment, we're actually using the feedback photon lots, billions of the cavity magnum polariton coherently. And because of that, we are able to reinstall, in my view, beautifully, this photon number control of the Rabi frequency in many spin systems. That is very fun. So the second take-home message is my perspective of cavity spintronics. Well, we can put that new field in the context of quantum technology. And people here knows very well, when you're developing quantum technology, you're using many, many different systems. If you characterize them using the eigenfrequency and the coherent time, then you find out the optical cavity has very high frequency, optical frequency, low coherent time. You have atoms at the optical frequency. You have optical fiber systems. You have a qubit based on superconducting systems. You have microwave resonator cavity. You have ferromagnetic spin. You have optical mechanical resonator, nuclear spins. People understand very well that to develop quantum technology, one system is not good enough. You have to find a way to coherently link different systems. And cavity spintronics or spin cavitronics is focused on coherently linking microwave cavity with the ferromagnetic spins. And by doing that, pioneers already demonstrated that we are producing this hybrid beast. What I'm trying to tell you in this lecture is that we should also perhaps look a little bit at the many-way system of this hybrid beast. And I believe there are a lot of new things waiting us to discover in this new field. So with that, I thank you very much for your attention. And